Today we are diving into one of the simplest but most powerful data structure you will ever use, stacks, right? Look at this. Can you take a book from the middle of this? No, we can't. Why we can't? If we take a book from the middle, the others can be fallen, right? Okay. We can insert to delete elements from one end. Look at this. We can insert a book only to the top, right? Okay. Stacks are sometimes known as LIFO lists, right? LIFO stands for last in, first out. It means we add an element to the top of the stack and remove elements from the top of the stack, right? Insert and remove, right? Stacks store a set of elements in a particular order. It uses last in, first out principle. It means the last element inserted is the first one to be removed, right? Normally, stacks are represented like this, okay? 1, 2, 3. Normally we can represent it, stacks are this, right? Okay. Think of adding an item to the stack. Adding an item to the stack is called push, right? See? Okay. Think of removing an item from the stack. Removing an item from the stack is called pop. In the popping, we remove the last item from the stack, right? This is the last item, okay? In computer science, we have to restrict insertion and deletion that takes place only at the beginning or the end of the list, not in the middle, right? What are the applications? Back button of web browser. History of visited web pages is pushed onto the stack and popped when back button is clicked, right? Undo functionality of a text editor and reversing the order of element in an array and saving local variables when one function calls another and this one calls another and so on, right? The ordinary stack is one of the most important data structures in all of computing, right? First one is function or method calls are placed onto a stack. Compilers use stacks to evaluate expressions. Stacks are great for reversing things, matching up related pairs of things, and backtracking algorithms, right? Stack programming problems are reverse letters in a string, reverse words in a line, or reverse a list of numbers, and find out whether a string is a palindrome. Examine a file to see if it is braces and other operators match, right? Convert infix expression to postfix or prefix, right? A stack is a linear data structure, right? That can be accessed only at one of its ends for storing and retrieving data, right? There are two ways of implementing a stack. What are they? An array and a linked list, right? What is an abstract data type? An abstract type is essentially a conceptual model or a blueprint for a data type defined by what it does rather than how it is built. An ADT defines the set of data values and the set of operations that can be performed on that data, right? It does not specify the underlying programming code or data structure like array or a linked list used to implement those operations. It separates the interface from the implementation. Interface means what the user sees and uses, right? Implementation means common ADTs include list, stack, queue, set and map. ADTs provide a precise, unambiguous way to define reusable components. Components mean modules that can be easily plugged into different programs, right? This makes code clean and reliable. Think of an ADT like a blender. ADT, the concept, a device that can perform the operation blend ingredients. It's defined by its function. It means what it does, right? Okay. Implementation. The how. This could be a cheap hand blender, a powerful Vitamix, or function remains the same, right? In programming, a stack ADT defines the operations push and pop. Whether you implement that stack using an array or linked list as a detail hidden from the user, they just use the push and pop operations, right? Stack follows these operations. The first one is push, which adds the item to the top of the stack, like this, right? After pushing an item to the stack, you can see added one on top of the stack. See? Okay. The next one is pop, which removes the item from the top of the stack, right? See? This time, the top item is 4, right? After removing it, the 3 is at the top of the stack, okay? If the stack does have nothing, we can say it is empty, which is called is empty. A stack reaches the maximum limit that it can have. Simply think, we can add a maximum of 4 items into the stack. In this time, stack filled with 4 items, right? Which is called as the is full, okay? If we get the top value without removing, which is called peak, right? See, without removing, we can write this, okay? The operations work as follows. A pointer called top is used to keep track of the top element in the stack, right? We start the process from an empty stack. Therefore, when initializing the stack, we set its value to -1 so that we can check if the stack is empty by comparing top is equal to -1, right? If they tell top is equal to -1, at this time stack is empty, right? Before pushing, we check if the stack is already full. See, we have 3 items, right? It is not full. The stack has not reached the maximum value, therefore we can add an item, right? Okay. On pushing an element, we increase the value of top and place the new element in the position pointed to by top, right? Okay. At this time, we had increased the top from 1. Minus 1 increased into 0, right? Okay. If we have an array named as stack, this means the stack array's zeroth index value is 1, right? Before popping, we check if the stack is already empty. It is not empty. Therefore, we can remove the item from this. Okay. On popping an element pointed to by top and reduce its value, right? Okay. After popping, you can see it like this, right? Conditions are this, okay? Static implementation can be done in 2 ways, right? First one, static implementation. In static implementation, stacks have a fixed size and are implemented as arrays. It is also inefficient for utilization of memory. In dynamic implementation, stacks grow in size as needed and are implemented as linked lists, right? Dynamic implementation is done through pointers. The memory is efficiently utilized with dynamic. Stack related terms. First one is top. A top is a pointer that points to the top element in the stack. See? Okay. Next one is Stack Overflow, right? We have the 4 items in the stack, which is the maximum that can exist, right? Can we add an item to it? Can we? No, we can't. Simply remember that if our stack is full, which is called a stack overflow, at this time, you can't add anything to the stack, okay? If the stack has nothing, it is called a stack underflow. See, stack has nothing, okay? In short, if the stack is empty, which is a stack underflow, right? Consider a stack with 4 elements. This is called the size of the stack. The number of elements to be added should not exceed the maximum size of the stack, right? If we attempt to add new element, think we add element like 5. Right? If we attempt to add new element beyond the maximum size, right, we will encounter a stack overflow condition. This is the stack overflow condition, right? Similarly, we cannot remove elements beyond the base of the stack, right? See, it hasn't any elements, therefore we can't remove anything, right? If such is the case, we will reach a stack underflow condition, right? Insert an element in a stack. We have to add a new value to the stack. Before it, we should check that the top is equal to max minus 1, right? Okay. Max means the maximum size of the stack. The total number of elements the stack can hold, right? But we have 5 items at this time, okay? We can add 4 more, right? Because we have 4 spaces, right? Okay. We can get the indexes from max minus 1, okay? We have 8 indexes, right? Max mean size of the stack. Top is 8 right now, okay? top is 4 at this time. Sorry. But we check this. Okay. This means the stack is full, right? If top is equal to 8, stack is full. But stack is not full in this time. Okay. We increment the value of top and store the new value. New value at the position given by stack, right? Because this condition is false at this time, right? Now top should be 5, right? Okay, we can represent it like this. Okay, this is the empty stack and we should insert 5 to this stack and 5 in this stack, and this is the top. Let's insert, let's push another value 5, 4 in this time. This is the top. Okay, and we can insert another value 5, 4, give it as 3. At this time, this is the top of the stack. Okay. In the popping, we must delete the topmost element from the stack. Consider this, right? We should pop the element, right? We should remove the topmost element, right? We should remove the topmost element. Topmost element is 3, therefore we should pop it. After popping, you can see 1 and 2 only. Okay, 3 is deleted, right? Can you delete anything from this? No, you can't. However, before deleting the value, we must first check if top is equal to null. Because if stack is empty, then no more deletions can be done, right? If an attempt is made to delete a value from a stack that is already empty, an underflow message is printed, we should delete the 3, right? Let's copy it. After deleting, you can see 1 and 2. 3 is out of there, right? Okay. To delete the topmost element, we first check top is equal to null. If the condition is false, then we decrement the value pointed to by top, right? Look at this diagram. The stack is not empty, therefore we can decrement the top value, right? After decrementing, the top value should be 2, right? 3 minus 1 equal to 2, right? And 4 is deleted, right? See, when an element is taken off from the stack, the operation is performed by pop, right? Okay. Peek operation. Peek is an operation that returns the value of the topmost element of the stack without deleting it from the stack. The peak has the boundary condition, right? The boundary condition we must check for is whether the data structure is empty. The boundary condition is data structure is empty, right? Why this is the boundary condition? If the data structure is empty, the peak operation cannot return an element as there are none to look at. Attempting to peek on an empty structure will result in an error, right? The isEmpty operation verifies whether the stock is empty. This operation is used to check the status of the stack with the help of the top pointer. The isFull operation checks whether the stack is full. This operation is used to check the status of the stack with the help of top pointer. What are the applications of stacks? Reversing a list, parentheses checker, conversion of infix expression into a postfix expression, conversion of an infix expression into a prefix expression, evaluation of a postfix expression, evaluation of a prefix expression, recursion, and Tower of Hanoi, right? Reversing list. A list of numbers or characters can be reversed by reading each number or character from an array starting from the first index and pushing it on a stack, right? How can we read this word? It has 7 characters, right? First, we should start from the first index. Read. First one is R. Therefore, we should add it into the stack, right? R. Read next one. E. Push into the stack. Next. V. Next. E. Next. R. Next. S. And the next last one is E, right? Now all are in the stack, right? Once all the numbers have been read, now we read, right? Okay. The numbers can be popped one at a time and stored in the array starting from the first index. First we should pop this. Therefore, now first element should be E, right? And secondly, wait, I erase it. This right. The next we should pop S, right? Therefore, S should be the next one of the new array, right? See, right. Erase it. We should pop R, right? Therefore, the next item is next item of the new array is R, right? Okay. Erase it. Now we should pop E, right? Add it into new array, right? We should pop V, right? And add into the new array. Like this. And we should pop E and add into the new array. We should remove the final one. Now stack is empty. Add it into the new array. Right. Now you can see the reversing, right? See? Okay. If you get something from this video, don't forget to subscribe us and share with your friends. This is the first part of stack, right? We'll meet in second part of this. Bye bye.